Hey there, everybody. I've got 5 exercises picked out for section 1.5 on trigonometric functions. So let's jump right in. Question 3, number 3 in the textbook says, for each angle, draw the angle using a ray through the origin. So we're going to draw the angle. And then we're going to determine whether the sine, the cosine, and the tangent are positive, negative, 0, or undefined. And the key is we're going to do it without using a calculator to see the actual numbers. We're just going to think about what sine, cosine, and tangent mean for that angle. So pi over 4, this is an angle that we saw in our lecture. This is a 45-degree angle. Now, if we had forgotten that, the way we would figure it out is we take pi over 4. We would multiply by our 180 over pi conversion factor. Let's remember why that's the direction we want. This is degrees, this is radians, and this whole thing is radians. So this makes sense because the radians will cancel out and leave us with a measurement in degrees. And we get the pi's that cancel. That leaves us with 180 over 4 degrees. To divide by 4, just divide by 2 twice. So 180 over 2 is 90. 90 over 2 is 45. So if we know that, then we know what our angle looks like. Let's draw our flat ray, that's our x-axis, and then let's draw one that's about 45 degrees. Now we're just kind of estimating here. The key part of doing this is figuring out which quadrant is it in. Remember that, the xy plane is split into 4 quadrants. Quadrant 1, 2, 3, and 4. And in order to know whether sine, cosine, and tangent are positive, negative, 0, or undefined, you need to know which quadrant you're in. For example, here, cosine and sine are positive. Here, cosine is negative and sine is positive. You don't need to memorize that. The way you know that is that cosine represents the x value and sine represents the y value. So if you're here, you have a negative x value and a positive y value, and so on. So here with 45 degrees, we're in this first quadrant. So we can imagine that we have our circle. Maybe I should have drawn the circle first, but let's draw it now. Try to fit this in here. Yeah, okay. It's not exactly going to work, but close enough. The point is that we've got our xy plane. Whoops. Please pardon the technical difficulties. We've got our xy plane. And where is this point? It's in the first quadrant. So clearly it has a positive x and a positive y. So cosine of an angle tells us the x component, and sine of an angle tells us the y component. So that means they're both positive. And lastly, we were asked about tangent. Well, remember, 2 ways you could do this. First, you could just realize that a positive number over a positive number is positive. Remember that tangent is defined as sine over cosine. But also, we said that tangent, another way to think about it, is that it's the slope of the line. So in fact, at 45 degrees, the slope of the line is 1, but you don't even need to know that part. You can just tell by looking at it, it's the slope of a positive line. So either way works to figure out the tangent is positive. Okay, that's problem number 1. I hope that you paused before I did it and tried it on your own before watching me do it. Let's move on to the second question. This is number 11, and it gives us a trig function with some transformations and asks us to find the period and the amplitude. So remember the period, that is roughly the distance between the x-axis, or wherever the middle point of your wave is, and the top, or the distance between that and the bottom, either way. Now, this one is shifted up by 5, but that has no effect on our amplitude. The amplitude is the distance from the middle to the top, wherever that middle is. Maybe even a better way to think about it is that the amplitude is half the distance between the highest and the lowest. So find your highest and your lowest and split it in half. But we have a formula for the amplitude anyway. The amplitude comes from looking at this vertical stretch factor. Remember, putting something in front like that causes a vertical stretch of your function. And we had a formula for amplitude. It's just the absolute value of that vertical stretch. I think we called this A in the actual formula. capital A, something like that. But in this case, it's just 3. The period, on the other hand, the period is how long it takes to go from a starting point, whether it's down here if it's sine or up here if it's cosine, and do one full rotation until you get back where you started. And the normal period of cosine and sine is 2 pi. So if you make no transformations, it takes 2 pi radians to get back to where you started. And that makes sense because a circle has 2 pi radians. So once you go all the way around, you're back where you started. But that's affected by this horizontal stretching or shrinking factor. Remember that this is dividing by 4. That's like multiplying by 1/4. So you can think about this cosine of u over 4, if it helps, as cosine of 1/4 times u. Okay, so what is that doing? That 1/4, that's actually causing a horizontal stretch because you're taking your input values not from where you are, but kind of from 1/4 of the distance you are. So, for example, if u equals, let's say, 6 pi, then we're looking at cosine of 6 pi over 4, which is 3 pi over 2. So you are kind of looking further away. Now we also had a formula for this. The formula was 2 pi over the absolute value of b, where b is whatever your multiplicative factor in there is, in this case 1/4. So with our numbers, that's 2 pi over the absolute value of 1/4. The absolute value of 1/4 is just 1/4 because it's already positive. So this is 2 pi over 1/4. Remember that when you're dividing by a fraction, you flip the denominator and multiply. So this is 4 times 2 pi, which is 8 pi. So you can get that 8 pi by using this formula, or you could just remember back from section 1.3 where we talked about all these transformations, that having a 1/4 multiplier inside stretches you out by a factor of 4. So if you're stretched out by a factor of 4 and it normally takes you 2 pi to do a whole loop, now it takes you 4 times that, which is 8 pi. You go way slower. It takes you a lot longer. So that's it for this problem. We've got an amplitude of 3 and a period of 8 pi. This vertical shift here had no effect at all on the amplitude or the period. On to the third one. Our goal here is to calculate a certain quantity. In this case, we're going to calculate sine of pi over 5, but we only have 2 pieces of information. They tell us to not use the trig functions on a calculator. We're still going to need a calculator, but not for the trig functions, just for some arithmetic. Now, if you could use the trig functions, obviously you would just plug it in. But here we have some information. We have sine of pi over 12 and cosine of pi over 5. And for these exercises from 24 to 29, depending on which one you're looking at, one of these might be the helpful one. In some of them, the other one would be the helpful one. Well, we've got a couple tricks here. One is that we have this identity we talked about, sine squared of theta plus cosine squared of theta equals 1 for all angles theta. So we're going to apply this now. What this really does is it relates sine and cosine. Now they have squareds there, but we know how to undo squares with square roots. So that's what we're going to do. We're going to plug in what we know for cosine. We know cosine of pi over 5. So let's write this. Since we know cosine of pi over 5, we can fill that in. We get sine squared of pi over 5. We want to know that. Really, we want to know just sine of pi over 5. Plus 0.809 squared equals 1. So let's rearrange and let's solve for the unknown of sine of pi over 5. First, we can move this quantity over to the right-hand side with subtraction. And lastly, this is the square of what we want, so let's take the square root of both sides. Oops. Now, here's where you need to be careful, because when you're taking the square root of both sides, you need kind of a plus or minus here. Because whether we choose the plus or minus, it's still going to be true that when we square it, we get this. Because squaring gets rid of the sign. If you square a plus, you get a plus. And if you square a minus, you also get a plus. So when you're undoing that, you don't know which one you came from, whether you came from the plus or came from the minus. So what we need to do is think about which quadrant we're in. If we think about our axes again, that's 0, that's pi over 2, and that's 3 pi over 2. So here we're looking at pi over 5. Well, pi over 2 is here. If you're dividing by 5 instead of 2, that means you're even smaller. So the angle that we're actually examining is somewhere in here. Now that tells us that we expect a positive sine and a positive cosine. And of course, we knew we had a positive cosine because it told us. But that tells us now which sign we want. We want the plus sign because we have a positive, because we're in this first quadrant. And sine is the y-coordinate, so it must be positive. So that tells us we're basically nearly done. That tells us our answer is 1 minus, so the square root of 1 minus 0.809 squared. And we didn't need the plus or minus because we just figured out the answer is plus. So if you plug this into a calculator, you will get approximately 0.5878. And that's our answer. Now, if we were in a different quadrant where sine were negative, like for example, if we were looking at sine of negative pi over 5, then you would have maybe a different answer for whether you pick the plus or minus sign. So for example, if it was negative pi over 5, that's going to have the same cosine because it's a positive x here and a positive x here. But up here, the sign was positive, and down here, the sign would be negative. So you really have to think about which angle your quadrants, which quadrant you're in, which quadrant your angle is in. There we go. Okay, moving on to our fourth question. We have an equation here. We have a variable x that we want to solve for, and that's basically it. The problem is that the x is inside of a cosine, so that's where we're going to need to use our inverse trig functions to get it out of the cosine. So if we're going to isolate the x, let's first move the minus 3 over to the left. That means we have 4 on the left-hand side equals 8 cosine 2x plus 1. Then we'll divide the 8 over. On the left, we'll have 4 over 8, which is 1/2. And now we've arrived at a place where the variable's inside of a cosine. So the only way that we can cancel that out is by applying the inverse function, which is arc cosine, to both sides. So this is kind of like in 1.4, where when we had a log, we could do a to the power of both sides to undo it. Or if we had an exponent, we could do the log of both sides to undo it. The inverse undoes the original function. So on the left, we have arc cosine of 1/2. On the right, we have arc cosine of cosine of 2x plus 1. And because they're inverses, those are going to cancel. So the right-hand side is just 2x plus 1. So to isolate the x now, all we have to do is subtract the 1 over to the left and then divide the 2. So we can do those both in one step, and we get that x equals arc cosine of 1/2 minus the 1 and then all over 2. If that's too many steps at once, because I kind of did two things at once here, just write them out both individually. You'll see that first you subtract the 1, then you divide by the 2. Now, I would consider this definitely a good enough exact answer. It says give it an exact form and decimal form. If you remember your unit circle from the last time that you took pre-calculus, you might remember that arc cosine of 1/2 is pi over 3. If you don't remember that, that's okay. For now, because I didn't tell you you need to know that, this is a good exact form. To put it in decimal form, you need a calculator that has an arc cosine button. The one that I've been showing you on screen doesn't, but this is where Google can do a perfectly good job. You can just type in arc cosine of 1/2 into Google, or Wolfram Alpha, or anything like that. So you've got a lot of options there. When you just plug this in and evaluate the whole thing, you get a decimal answer of approximately 0.0236. And so that's our answer. So we solved for x, and the only kind of new thing we had to do here was use this arc cosine function. All right, last one, fifth problem. This is one of those near the end of the section that tells you something, and you have to explain what's wrong. So what it claims is that the functions f of x equals 3 times cosine x, and g of x equals cosine of 3x have the same period. Now, let's just be clear about what these functions are. I don't like when I see trig functions without the parentheses because it's kind of needlessly ambiguous and confusing, and the parentheses don't cost that much extra money. So let's just add in our parentheses. And now we see we definitely have two different functions. But why don't they have the same period? So let's think about this. Let's draw cosine of x first. Just a really rough drawing. It starts at 1 and does this kind of shape. I've only drawn one period there, but it has amplitude 1 and it has period 2 pi. Now let's think about what 3 cosine of x is. We remember from section 1.3 about our transformations that if we're multiplying by a 3 in front, that's a vertical stretch by a factor of 3. But it has nothing to do with a horizontal stretch. So instead of being at 1, it starts at 3, and we'll go all the way down to negative 3, but has the same period. It goes through 0 at the same spot and looks kind of like that. That's 3 times cosine of x. So this multiplication by 3 means the amplitude has now increased to 3. From the baseline to the top is 3. But the period is totally the same. Okay, that's f. Now lastly, let's look at g. This is multiplying by a 3 inside. Now you have to remember what that does. Multiplying by a 3 inside means that when you're evaluating cosine of 3x, you're pulling your values from further away. So you're kind of bringing all your far away values in close together. And so you're making your same function but narrower. You're doing a horizontal shrink. So it has a 3 inside but not outside. So it starts at 1 and it does the same kind of thing, but it does it much faster. It does it 3 times faster. So it looks something like, let's see, probably something like this. So this is cosine of 3x. Clearly, the period is not the same. The period is how long it takes to get back where you started. This took 2 pi, because that's our period for cosine. So this is 2 pi here. But this reaches it 3 times faster, because we've got this horizontal shrink. So this period is not 2 pi, it's 2 pi over 3. So that is, let's label it. That's cosine of 3x, which has amplitude 1 and period 2 pi over 3. So what's wrong with the statement? I exactly don't know how to phrase this, but the statement is wrong. This has a period of 2 pi. This has a period of 2 pi over 3. So they don't have the same period. Okay, that's it. I've suggested a couple problems on the website like normal for this section. The problems in 1.5 are all kind of basically the same. So once you do a couple of them and get the hang of them, you should have no problem with these.